Okay, you want to ask this question. Remember, this is group. It's a discussion about undergraduate course in group theory, and we want to look at some of the common groups that we normally have. I will start with a question. I want to pause. If you look at this group, okay, that non-empty set, so integers set module n. This is a group of all n. This is actually, so this we believe this is a group. It's a group. It's a group. It's a group of for all n numbers where addition in this case is done modulo n. So the addition here is done modulo n. So that's what we mean by that. Now, if we check this for sure is a group. It's a group, meaning we can check on how the inverse. So if m is of this set, okay, is of that set, then obvious what you know here is that m, negative m, will be n minus m, which should be the inverse of this set, that element. So we are basically getting the m, and we take n, the modulo the n, then we take away the m, and therefore you'll be able now to get the inverse of that particular element. Okay, so having said this, we can now ask our question, pose this question. We can ask this question. What about this particular set z, the integer set module n under multiplication? Is this a group? We can ask ourselves, is this a group? Is this a group? We can investigate and see whether this is a group or not. How will we do this? We'll consider a given set here. We can use z mod n and the division. And for us to investigate this, we need to use the idea or concept of a table we normally refer as Cayley table. Use the Cayley table. This table here, we'll have to first identify elements of z mod 8. These elements of this set is actually 0, 1, 2, 3, 4, 5, 6, 7. So that is actually the module. This is gotten from the concept that in case we have this kind of set, the zn, then the integers will be 0, 1, okay, that way, 2, the last integer will be n minus 1. That's the general definition of this set, this kind of set. So after learning that from this, we can now introduce the Cayley table. So the Cayley table, we draw it like this. Okay, and we put the identity, the binary operator there. Then we cross one, the elements, we cross them. 4, 5, 6, 7. We do same here. 1, 2, 3, 4, 5, 6, 7. Remember, if you have not subscribed to this channel, kindly subscribe, and it will be helping you to do this kind of problems. It's a very interesting thing, and we like them. We all like maths. So this one, if you do this and this to this, you are getting automatically that happens. Remember, it's module 8. It's module 8. Down this is also happening. Remember, I'm just doing 7 by 0. That's 0 automatically. Okay. The next thing I do 1, 2, 2. Sorry, I forgot something here. Yeah, there. Let's put something here. 1 there. So I did zeros. These zeros. So I am doing 1. I'm doing 1 and 1 now. 1 and 1 now. So that I have 1 and 2, 2, 3, 4, 5, 6, and 7. Okay. I do again with the 1, 1. So 2 goes 2, 3, 4, 5, 6, 7. Remember, it's module 7. Okay, so the next thing I do now is 2 by 2, and that gives me 4. Okay, 2 by 3, I get 6. Okay, then I do 2 by 4, 8. So 8 mod 8. Okay, that's like 8 minus 8. 8 minus 8. You see, I'll get 0. Because 8 minus 8 is 0. Okay, 8 mod 8. The remainder is 0. That's what you mean. So if we are looking at the remainder, so you are doing the remainder. If you do 8 by 8, you get 1. Remainder 0. So this 0 is what we are called the mod. Okay, so it's the answer that we are going to put here. Okay, so then we do 2 by 5, that is 10. So 2 by 5, that is 10. So if you divide by 8, it will go 1, remainder 2. So the answer here becomes 2. Okay, so that's the concept. Then 2 by 6 is 12. 2 by 6 is 12. 12 divided by 8, it will go 1, remainder 4. So here we get 4. Then you do 2 by 7, get 14. Divided by 8, we get 1, remainder 6. So 6 there. Okay. So what you'll learn is that if this part goes like this, the down part also follows the suit. So I expect this one to be 6. I expect this one to be 0. I expect this one to be 2. I expect this one to be 4. I expect this one to be 6. We are basically using the same concept here. Okay. So let's now go to 3. 3 by 3. 3 by 3 equal to 9. 9 divided by 8 is equal to 1, remainder 1. So here will be 1. Okay, that's 1. Then we do 3 by 4. 3 by 4, which is giving us 12. We're giving 12. 12 divided by 8 is 1, remainder 4. So here is 4. Okay, that's 4. We do 3 by 5, which is 15. Okay, 15 divided by 8 is 1, remainder 7. So this becomes 7. Okay, then we do 3 by 6, 18 divided by 8, you get 1, okay, 2. Is it true? 16, remainder 2. So this becomes 2. Remember what you said. If you have any question of either of these calculations here, just leave a comment. If you find another question that's challenging, leave a comment there. Remember to show your friends. Let them know that our channel which is friendly and it's guiding you step by step without any hurry. Slow but sure. And it's very live, huh? It's live. Okay. So 3 by 7, that is 21 divided by 8. And this becomes 2 times 2, 16, remainder. Remainder 5. So this becomes 5. So that's happening. That's true. That's true. So as we have said, these concepts go first. So this will be 4. This will be 7. This will be 2. This will be 5. Now the others will fall like this. It fall like this. Now we have known how to do this. 4 means 0, 4, 0, 4. So this is 4, 0, 4. Okay. This one will be 525, which will 1, 1, 6, 3. So this becomes 6, 3. This will be 6 by 6, 36 by 8. We can go in form because of the other 2, 4. Okay, then 2. Then we go 2 here. Okay, and you see 7 by 7, 49. 49 by 8 divided by 8. We are having remainder 1. Remainder 1. Okay. Remainder 1 be remainder 1. So that is actually the card table. So we have found the whole card table here. So our next interest here will be now to see whether the rules of a group are holding. Whether we can trace inverse, particular inverse, and their identities. If that is happening, then this becomes a group. But if it does the own, then we'll have no doubt but to say this is not a group. So let us observe what is happening. What's happening? So here I introduce the element. Okay. Reduce the element. So that we are able now to see whether all of them they are here, and we see whether you can identify the inverse. So what we are doing, we are having 0 there, 1, 2, 3, 4, 5, 6, 7. So if we are looking at inverse, we believe that the inverse of multiplication, the identity should be 1. Sure. Yeah, should be 1. The identity should be 1. So we are looking at the multiplication here on where we have 1. So you can see 1, 1. So the inverse of 1 is 1. You can see that. Anything that we are multiplying by it's something 1, we are multiplying by something, we get the identity 2. Okay. Yeah, so it's 1. if we look at 3, you find that if we want to get this, the inverse, get the identity, you see is 1. We are still multiplying with 1, 2. Number multiplying by the identity, you get the number. So you can see 3 by the number, you get 1. You see 3. So the inverse here is 3. The inverse of 3 here is 3 because it's giving us the identity. 4. The inverse of 4 is not there because we can't see anyone here. The inverse of 5 is actually 5 because it's giving us the identity 1. You see, just like that. The inverse of 6 is not there. We can't get the identity. We can't get the identity. The inverse of 7 is actually 7 itself because you can get the identity here is 1. So that's what you are saying. The inverse of 3 itself, the inverse of 5 this, the inverse of 7 is this. Here, none. We have seen that. By elimination, it's none. None. So it's as simple as to treat like that. So what we can see from this table is that this group here, it is not this one, this set here, this algebraic structure here. I'm giving them a wrong name. it's not a group by the fact that all the elements doesn't have the inverse. They don't have the inverse, and that we have gotten it from the Cayley table. So this tells us that if we can get what we call coprimes, because the coprimes are actually here. The coprimes is 1, 3, 5, and 7 in this group. All these coprimes, they are elements which, if we get the GCD of these, the answer is 1. They have a common GCD of 1. So they are having, if we take this group here for coprimes, we are seeing clear this is actually a group. Why are we saying it's a group? Because all of these elements have their inverses. They have inverses, the inverses are present. So this means a coprime group in a coprimes point to these coprimes, they are group. They are making a group with a very interesting property, which we call self-inverse. Self-inverse. They have self-inverse. So basically, generally, if you have this kind of algebraic structure, this will be not be a group. You have to note that. But its coprimes relative to the n, this for monthly, okay, monthly, will be a group, okay, and you have seen that will be a group whose inverse is self-inverse. And having noted that, because you have noted that, it will mean that that's a very interesting thing in group theory, and kindly have a note on it. And if you have really understood this fact, kindly leave a comment there, and we'll be able to check on you. Okay, again, share with your friends, and don't forget to subscribe. This is Davika Academy. Kindly subscribe and share a lot. Okay.